In the previous couple of lectures, we saw that there is a singularity at the contact line. This singularity is sometimes referred to as the Herns-Scriven paradox. There has been a lot of research on the subject of moving contact lines, primarily because of the singularity, and we will look at some of the ways in which scientists have attempted to alleviate the singularity. And we will look at one simple mechanical model which basically gives us a relationship between the force and the velocity, or in particular, it gives us a relationship between the velocity of the moving contact line and the contact angle theta. Of course, this is a dynamic contact angle, and we will see a very simple model. This model is thanks to the physicist Degennes, and we will revisit this problem, and the problem is discussed in more detail in a book that he has authored, which is also a reference book for this course. So let us basically look at some of the standard ways in which people have tried to elevate the singularity of the contact line. So let's consider the problem that we were looking at. So we have this is a problem that we've already studied. It's a thin film that is flowing down an incline. This is the incline. And I already said at this point, that's the position of the contact line. At this point, there is a singularity, right? If you apply the no-slip condition and so on. So what are the ways in which people have tried to address alleviate the singularity? The first kind of approach is to say that, well, if the contact line is the singularity, the presence of the contact line is the cause of the singularity, how about not having a contact line at all? And how do we do this? You basically put a thin precursor film. You put a thin precursor film in front. Let me make sure that, yeah, okay. Ahead of the contact line. So what does exactly this precursor film? Let's consider a thin plate like this, and we have a contact line problem. Well, if you notice carefully, I haven't really completed my drawing for a very good reason. The argument is that when you approach the contact line, then beyond this point, there is a very thin, microscopically thin film that is in front. And this thickness of the film is unknown, has to be determined as part of the solution. This thickness of the film, let's call it as delta. And the argument is that if you basically have a very thin in front of the contact line, then you don't need to basically deal with the singularity at the contact line, right? So this is basically the precursor film model, and one can actually, the exact problem of thin film down an incline that we have studied with the singularity has been attempted by several scientists using this precursor film approach. Now the other approach, and I'll quickly go through the various approaches in the problem. The other approach is a slip model, and there are a variety of slip models, but by and large, the main feature of these slip models is as follows. So again, let me draw the same. You have a plate that is present there, and on this plate you have a contact line that's present there. The argument of the slip models is there is a certain region, let's say on either side, let's say this is x1 and this is x2, and this is my contact line position. This region is basically called a slip region. So, and on either side of this condition, you apply the no slip condition. So the slip models are very, very popular because they are easy to apply, but they have their own challenges when it comes to numerical simulations. But most of the numerical simulations, numerical tools that are available, numerical softwares are solving for which involve problems in moving contact lines. They have a numerical version of the slip. So that's another way to justify these kinds of slip models. Now, the commonly used, let me first write it down, assumes that there is a small region near the contact line where we can relax the no slip condition. The exact details vary from between various slip models, but the general feature is that there is a small region within which you can relax a slip model, and the common slip model essentially says that you can common slip condition. Let's put it this way: common slip boundary condition that one can employ would be the Navier slip condition. So you see at the contact line, near the contact line, for y on the solid, which is y equal to 0, you say there's a slip coefficient times del u by del y. So Ls is a slip coefficient. And if you actually if you put in the slip coefficient, then you can actually say the viscous stress for a flowing film of thickness h. If you have a flowing film of thickness h, then the viscous stress would essentially be 3 mu uc, where uc is the speed of the contact line. Now we have slip there, so if you solve the same problem with a slip, then you get this h plus 3 ls. So which means that when h goes to 0, the denominator does not go to 0, and this allows me to calculate the rate of dissipation. And dissipation, let's call it as E dot. This becomes 1 by 2 half uc square, and we have an integral which is over this quantity here, and this would be h plus 3 ls whole square, something of this nature. And we integrated along the thing, and the most important thing that I want to emphasize here is that this integral converges as h goes to 0. So this is basically how the slip models alleviate the singularity, because if you recall, what we said is that we got this singularity as h goes to 0 because the shear stress goes like 1 by h naught, where h naught is the thickness. So what you now say is that in the precursor film, h naught itself will never go to 0 because you have a thin film that is present, whereas in the slip model you calculate the shear stress including you relax the no slip condition. Okay, so they have some common features, but you see that both these models take slightly different routes to address the same issue, which is the issue of singularity at the contact line. Now the third kind of approach, which is to incorporate a new physics. near a contact line. Now there are broadly two approaches. The first one is it treats the contact line as treats a contact line motion, to be specific, as a thermally activated process. So small fluctuations in temperature basically alter the interactions between the interactions between the solid and the liquid, and these interactions will basically allow the contact line to keep jumping a little bit. So there is an energy barrier. Once that energy barrier is crossed, then then it allows the contact line to jump a little ahead. So the number of there are a large number of such jumps that occur, which results in a macroscopic motion of the contact line. So let me just write down what I just said. So this model treats the contact line motion as a thermally activated process. The contact line moves by small jumps due to thermal fluctuations. And the relevant length scale of these jumps is, let's call it as LT, because it depends on the local temperature. This would be the thermal energy, kBT, divided by the surface tension. And this quantity is of order of angstroms. So in other words, there are very, very tiny fluctuations that occur. And now we can calculate from this, we can calculate the speed of the contact line. The speed of the contact line will now be something like 2 times xi nu, where xi is basically the scale, it's related to the size of the jump. Then this is a generic feature of this model. So we have xi square of, then we have a driving force. The driving force is really because of an imbalance in the angle between the equilibrium angle and the exact angle, the apparent contact angle. Once this difference is there, then the contact line will move. So in other words, as I understand it, the contact line moves because of tries to relax towards the equilibrium angle, and the difference between these angles becomes a driving force for this motion. And so this is the form of the model, and this quantity that you see here, this nu that you see here, it's nothing but frequency at which energy barrier is crossed. This is a very, very large number. The idea is that this number of frequency is very, very large, but the actual jumps are very, very small. And therefore, in fact, if you see the product, xi has a length and this has a frequency. So in other words, you have very, very, very large such energy barriers that are crossed, and which results in tiny microscopic motion. But since if you average it over a finite time, then you see a macroscopic motion, because there are tiny fluctuations that occur, and very, very tiny fluctuations, but innumerable number of them. That's the idea. So there is an energy barrier that has to be crossed, and I won't go into too many details about this model, but this was first published in 1969 by Blake and Haynes. Now there is another model which is a lot more recent than that. This is the interface formation model. And this model essentially was proposed by Professor Shukmurzev. Maybe I should mention a few things here. The slip models, one of the most popular slip model is the so-called the Cox model. We also have the Degennes model. We look at the Degennes model in today's thing. This is done by the MKT. This is also called the molecular kinetic theory model. Degennes calls it the chemical model because of the chemical interactions between the solid and the liquid. This was by Blake and Haynes in 1969. And this is by Shukmurzev, and this is over several papers. If I recall correctly, 1997 is one of the important papers, but then there are several other papers, 93, 97, and then there is a book on the interface formation model. What is the idea of the interface formation model? The model essentially treats the surface tension. It basically looks at an interface when an interface is present near the solid. The idea is that every time the interface moves, overall the contact line moves, a new interface is created at the region, and this results in mass transfer between various phases. And one of the interesting things about this model is that the surface tension is treated as a dynamic quantity. It is allowed to relax over some characteristic scale some relaxation time scale. So in other words, normally what we have done is that surface tension is constant unless it is affected by temperature or surfactants, which leads to Marangoni stress. But this takes a very different approach, that if you actually approach very close to the contact line, the surface tension itself cannot be treated as constant, but relaxes very rapidly towards its equilibrium value far away from the contact line. And the model basically has, in the recent years, the model has had several successes in terms of experimental support. The model has got in very recent years. And then there are other models, primarily popular with people doing numerical simulations. This is the diffuse interface model. The diffuse interface model essentially says that if you look at a region very, very close to the contact line, the argument is that if you look at this region close to the contact line, the interface is actually not, you can treat the interface as having a finite thickness. So the interface width, let's say it is xi, that is interface width. There is another independent parameter called the diffusion length. These two parameters affect the motion of the contact line, and the generic version of this model is the driving force, which is the difference in the angle between the apparent contact angle that you see and the equilibrium contact angle, is of the order capillary times xi by LD. So this is the generic version of this model, and it's very popular with people doing numerical simulations particularly. So we've looked at a few of these models, and going into details of these models is certainly beyond the course, beyond the scope of this course. Further, one can spend an entire full course only discussing contact line models and how the mathematics behind the contact line models, but that's clearly not my intention. Therefore, I will leave it at that. So we'll look at one simple mechanical model. This is thanks to Professor Degennes. So the idea is basically the following. So this is Degennes' model. So let's quickly understand what is the Degennes model about. So let's say we have a flat surface like this, over which, and let's say this is x, over which there is a contact line and an interface like this. So we'll call this angle as theta d. That's the angle that the contact line, the interface makes with the wall. This is basically the dynamic contact angle. Now, we can actually further suppose that theta d is very, very small. So this is sort of a special case in which we are analyzing this model. We'll also say that if theta d is very small, tan of theta d is also very, very small. We'll also say that there is another, in the absence of any motion, the interface basically has a different angle. Let's call that as theta e. That's the equilibrium angle. We will also say that the equilibrium angle is also very, very small. So therefore, tan of theta d is theta d, and tan of theta e is also theta d, and tan of theta e is approximately theta e, right? So what is the model primarily about? It says that there is an unbalanced contact line force at the contact line, and if we have an unbalanced contact line force, and if the contact line is moving, then this product of the force times velocity, which is the work done, or the rate at which work is being expended, has to be exactly equal to the viscous dissipation that is being caused inside the fluid. So the viscous dissipation is basically causing us to expend a certain amount of energy to move the contact line. So in other words, I can simply say F times U will be a phi, where this phi is a viscous dissipation. F is unbalanced contact line force, and V is velocity of contact line. Now we can actually write down a simple expression for this contact line force. The contact line force can be thought of as, let's say in the static case, when there is no motion, we have gamma s minus gamma sl minus gamma cos theta d. But we are trying to take the same form of the contact line, the force, and so this is inspired from the Young's law, but the only difference is now we have a cosine of theta d. But we also know from Young's law that gamma s minus gamma sl is gamma cos theta e, right? So this essentially becomes gamma cos theta e minus gamma cosine of theta d, right? So this is gamma times cosine of theta e minus cosine of theta d. That's the force. Okay. And the question is, how do we estimate phi? Phi is basically viscous dissipation in a narrow wedge near the contact line. So I hope you can see where I'm trying to go with this. So I have written, if we can write the force in terms of the angle, the contact angle, and if I can write phi in terms of velocity, then I already have a relationship between force times velocity, and on the right hand side, if I can get some velocity terms, then I can I can express force in terms of a velocity. I can relate force to velocity, or more specifically, angle to the contact line velocity. Okay, that's the idea. Okay, so let's look at this. How do we estimate phi? The argument is as follows. So let's consider a simple flow inside a wedge. We've already seen in a few cases that the flow inside a wedge is given by a parabolic velocity profile. But if you make the wedge very, very narrow, then, and if you say that the angle is theta d, then the velocity inside this wedge can be approximately thought of if the contact line is moving with a certain velocity, then the entire interface is moving with a velocity of capital U, then you can say that the local velocity would be a simple Couette flow. It's a simple shear flow there, linearly varying velocity profile, where the vertical coordinate will take it as z, and we'll take x starting from here at the contact line. So you have x equal to 0 and z equal to 0, and at any location x we can write down the velocity, and that will be, we can assume it to be the dominant velocity profile would be a simple shear flow. So what we're really saying is that the entire contact line, the interface, is moving to the right with a certain velocity, which induces a motion inside this narrow wedge. Okay, so we know that from fluid mechanics, we know this dissipation phi is related to the stress tensor and the strain rate tensor in this form. And if you write down the main dominant terms in this corner, then the main dominant terms would simply be, by the way, this has to be integrated over the corner, and this would be the shear stress, that is mu times del u by del z, times the strain rate, the dominant strain rate, del u by del z. Now we'll just make an estimate for del u by del z. Del u by del z would simply be u over z, where the idea is that this height approximately is z, and at any given height, and therefore you can estimate shear stress to be like this. But if you think of it like a triangle here, because it's a wedge, if you say that this is x and this is z and the angle is theta d, we can simply write tan theta d will be z by x, and therefore z is equal to x tan theta d. Okay, and we also already said for theta d very, very small, we have z is approximately x times theta d, because tan theta d is approximately theta of d, and therefore I simply have del u by del z would be z, and z essentially becomes x times theta d. That's what we have. So we can now integrate this as follows. This is integrated over the corner, mu times u square by theta d square x square. Okay, this is integrated over the corner, and if you want to be more specific, this essentially becomes x going from 0 to infinity dx, z going from 0 to theta dx, and remember this x as infinity is should be interpreted as some length scale much larger than the contact line. We will actually come to that in a minute. So it's really not infinity, but we'll have to truncate this integration So we have mu times u square by theta d square x square dz, and this essentially gives me x going from 0 to infinity u square by theta d square x square of theta dx, right? And therefore my dissipation essentially will be mu u square by theta d 0 to infinity dx by x. Okay. Now this integral that we have here, we have to truncate this integral because it diverges at both ends. So we'll have to truncate this integral as follows. Truncating on the upper side by length L, and this length L, say size of the drop. So obviously when you do a problem like this, and if you're analyzing flow in a wedge, there is a macroscopic length scale that within which the equations have to be integrated. This quantity has to be integrated. You clearly cannot go to infinity. So there is an upper limit coming directly from the physical limitations of the problem. And on the lower side, on the lower limit, we use a molecular size. Say A, and we'll come to what this molecular size could be. So if you write down this quantity, then we simply have mu u square by dx. Now you have a to L dx by x. Okay, and this simply gives me mu u square by theta d, mu u square by theta d times logarithm of capital L by A. Now this logarithm of capital L by A, we can define it as L. So this is nothing but mu u square by theta d of L. So one can actually calculate what is the value of L. Now we've made some important assumptions, or rather Professor Degennes has made some important assumptions. The coefficient, this L, it can further depend on the velocity, the small l that we've written down. It can further depend on the velocity itself, and it could depend on the angle theta d itself, and there is some evidence apparently for the dependence of L on the velocity, small l on the velocity, but we will stick to what we have for the simple version that we have here. And therefore we have now an expression for the dissipation involving velocity and theta d, right? So this quantity A that I glossed over, this quantity A is like a slip length. Okay, so A is like a slip length that is present in the problem. And so now that we have phi, we have force. Now we can use the expression F into U will now be mu times U square by theta d times L, right? And if we use the expression for F, which is nothing but gamma times cosine of theta e minus cosine of theta d times U, will be mu U square by theta d times L. Now we can make some more simplification with this. If theta d and theta e are small, then cosine of theta e can be simply taken to be 1 minus theta e square by 2 factorial, and well, I'll just say 2 plus 1, and cosine of theta d is nothing but 1 minus theta d square by 2 plus 1, and this immediately gives me cosine of theta e minus cosine of theta d becomes theta d square by 2 minus theta e square by 2 at leading order, basically. Okay, and this immediately gives me gamma times theta d square minus theta e square by 2 multiplied by velocity will give me mu u square by there should be theta d, sorry, theta d times this L, right? Or in other words, I can simply write, I can cancel out one u here, and now I have, on the right hand side, I have mu u by gamma. That's what I have. This goes like 1 by 2L times theta d square minus theta e square. And this is nothing but a relationship between the capillary number and 1 by 2L theta d times theta d square minus theta e square. This is what the model gives, and the model predicts that the dynamic contact angle goes like capillary power 1 by 3, because notice that we have a theta d cube on the right hand side. So if I basically consider the relationship between, if I ask what is the relationship between theta d and the capillary number, and that turns out to be theta d cube, or in other words, the velocity, you can also say the velocity of the contact line, which we called it as u, I'll call it as uc, that again goes like theta d cube, right? So this model of course is valid when theta d is very small, but it makes at least the prediction that experiments have observed, that there is a relationship between the theta d and velocity, that the theta d goes like capillary power 1/3. Of course, these experiments are there are several experiments which show more other kinds of behavior, and therefore the model itself has limitations, but that's understandable because several important assumptions were made during the derivation of this model. In fact, one of the assumptions we made was that the angle has to be very small, and I was talking about one of the slip models by Cox. The Cox model sort of does not require this angle being small. Of course, there are more generic models which of course can be applied to a much wider range of angles, but they also come with sufficient complexity. So I will not be able to go into a discussion of those models in this course. So this sort of with this lecture we sort of come to the end of the course, and I hope you've stuck around till the end, and I also hope you've learned a lot of new things, and I hope to interact you during the course as well. And feel free to write to me if you have any specific questions about the course. So thank you, and all the very best.